This is going to be an introduction to the concept of stoichiometry, which is covered in chapter 5 of the textbook. In stoichiometry, we can relate the amounts of different reactants and products in a reaction. So for example, we could calculate how much product could be made from a certain amount of a reactant reacting. Or another example would be, say, how much of reactant A would you need to react with a certain amount of reactant B? And the picture there of that rocket taking off I took from the beginning of the chapter in the textbook, and the point here is that in rockets, a certain amount of fuel must be mixed with oxygen, usually liquid oxygen, in just the right ratio. So stoichiometry calculations would allow us to calculate what is that ratio of fuel to oxygen that would be needed. So stoichiometry is based on the balanced chemical equation, because remember, a chemical equation, when we put the coefficients in it, it tells us the relative amounts of the reactants and products, and that's illustrated in this chart from the textbook. So for example, the equation could relate the amount of formula units of A and B, where A is a reactant or product and B is another reactant or product from the reaction. But remember, generally, we don't think about formula units or total numbers, say, of molecules, for example. We usually think of moles. So we want to think of a chemical equation as giving the ratio of the moles of one substance in the reaction with the moles of another substance. So as an example, let's look at a reaction, the combustion of propane gas. Propane has the formula C3H8, and we know that when hydrocarbons burn, they produce carbon dioxide and water. So here is the balanced equation for that reaction. So we want to treat the coefficients in the balanced equation as moles. So we would interpret this reaction for the stoichiometry, we would say that when 1 mole of propane reacts, because propane has a coefficient of 1 here, each mole of propane needs to react with 5 moles of oxygen. And then 1 mole of propane would go on to produce 3 moles of carbon dioxide and 4 moles of water. So we want to treat the coefficients in the balanced equation as moles, and so therefore we can think of the balanced equation as a conversion factor between the moles of any reactant and any product in the reaction. So let's do a few examples of such a calculation. So again, using this reaction of propane burning and this balanced equation, we could ask, how many moles of carbon dioxide would you get if 2 moles of propane reacted completely with oxygen? So we're assuming here that we have enough oxygen to react with the propane, so we're not worrying about the amount of oxygen. But in the next section, we'll look at what happens when we can't make that assumption. But for now, we're assuming we have enough oxygen. So as we just saw, every mole of propane is going to produce 3 moles of carbon dioxide. Okay, so if we have 2 moles of propane, the balanced equation tells us that you're going to produce 3 moles of CO2 for each mole of propane that's reacting. So therefore, the amount of CO2 you're going to get is just 3 times the amount of propane that we started with, which is 6 moles. Now let's look at a slightly more complicated example. How about how many moles of CO2 would you get from 2 moles of oxygen reacting? So now we're assuming that we have 2 moles of oxygen and enough propane to react with that oxygen. So it's exactly the same idea as above, it's just the numbers aren't quite as easy. So the propane to CO2, it was a 3-to-1 ratio, so we just had to multiply the moles of propane by 3. Here it's a little more complicated, but we can apply the same idea. So in this case, we have 2 moles of oxygen. We can see the relationship is that 3 moles of CO2 are produced for each 5 moles of O2 that react. So all we do is just do exactly what we did above, and we're going to have the 3 moles of CO2 on top, but just on the bottom, now we would have the 5 moles of O2. So again, when you do this conversion, you just plug in the coefficients from the balanced equation to relate the moles of each reactant and product. And so that works out to be 1.2 moles of CO2. So 2 moles of oxygen reacting would produce 1.2 moles of carbon dioxide. So again, we can use the balance equation to relate the moles of any reactant or product with another reactant or product. But we would also like to be able to relate grams of a reactant and product. Because remember, grams is something that we can often measure directly. It's not usually easy to measure moles. So let's look at calculations now involving grams. And so I'm going to go to a slightly different reaction and look at the combustion of octane. Octane has the formula C8H18. It's one of the components of gasoline. And so here's the balance equation for octane. It's going to produce, each mole of octane is going to produce 8 moles of CO2 and 9 moles of water. And then you would need 15.5 or 25 over 2 moles of O2 to balance that. Again, if you don't like the fraction, just double all the coefficients. That would give you this equation. You can use either equation for this calculation. In my example, I'm not going to involve O2 anyway, so I'm just going to use the first equation because it makes the numbers simpler. And my example is, how many grams of carbon dioxide would you get from 50 grams of octane reacting with enough oxygen? So remember, the balance equation relates moles of reactants and products. It does not relate grams. So in order to answer this problem, we need to convert that 50 grams of octane to moles. And of course, to do that, we need to know the molar mass of octane. So calculate the molar mass of C8H18. And you get 114.2 grams per mole. You might want to check that calculation, confirm you get the same number. So we can take the 50 grams of C3H8 and divide by its molar mass, 114.2 grams per mole. And that gives us 0.438 moles of octane. And over here, that, of course, that should be C3H18. Okay, now we can do what we just did on the previous examples and use the balanced equation to relate moles of octane to moles of CO2. And we can see that 8 moles of CO2 are produced for each mole of octane. So I can take the moles of C8H18 and multiply by 8 moles of CO2 per each 1 mole of C8H18. And if you want to use the second equation with all whole numbers and use a 16:2 ratio, it doesn't matter, you'll get the same answer. And that works out to be 3.50 moles of CO2. So 50 grams of octane would produce that many moles of CO2, but the question asked how many grams of CO2 would we get. So now we just use the molar mass of CO2. CO2 has come up before, it's 44.01 grams per mole is its molar mass. So we just take 3.5 moles of CO2 times the molar mass, and we get 154 grams of CO2. Okay, so we have calculated that 50 grams of octane would produce 154 grams of CO2. And does it make sense that the mass is tripled pretty much? Well, actually it does, because if you think about what's happening is all of the 8 carbons in C8H18 end up in CO2, and now they all have 2 oxygens associated with them. Those 2 oxygens weigh a lot more than the hydrogens that were lost, so it makes sense that the mass would increase like that. Okay, so notice that it took us 3 steps to go from the grams of octane to grams of CO2. And I've rewritten that here in the sort of format that we've seen before for doing dimensional analysis. So I've written it all out. So, but it's the same idea. So we took the grams of octane and divided by the molar mass of octane. Notice that that cancels the grams of octane and gives the moles of octane. Then we use the ratio from the balance equation to go from moles of octane to moles of CO2. So that cancels the moles of octane. And then finally, we use the molar mass of CO2 to go from moles of CO2 to grams to get our final answer. And that is summarized in this chart from the textbook, you can relate the grams of any reactant or product A with any other reactant or product B. Again, you go through 3 steps. You start with the mass of one, convert that to moles, use the balanced equation to go to the moles of the other one, and then finally, using the molar mass, go back to the mass of the other product. This is sometimes referred to as a grams to moles to grams, or for short, GMMG calculation. So notice that is what we're doing. You always start with the grams of one, go to moles, use the balanced equation to go to moles of the other thing, and then finally go back to grams. Notice that we cannot go directly between grams, between mass of one thing and mass of something else. You always have to go through moles.